tonight's webinar is Creating a Healthy Soil Using Soil Amendments. It is one of the many free webinars that we're offering this year and next year in a series called A Focus on Sustainability. This series was developed by a group of organizations known regionally in the United States for their quality education programs. We're working together to expand the reach of these programs through our webinar series. If you're not familiar with our organizations, we're all nonprofits and largely volunteer groups. And we are the Ecological Landscaping Association in the Northeastern U.S. And tonight, Risa Edelstein is an assistant for this webinar. I'm with the Chesapeake Conservation Landscaping Council in the Mid-Atlantic area. Our presenter tonight is with the Midwest Ecological Landscaping Alliance, MELA, and also part of the group that's cooperating on this effort is the Ecolandscape California. So tonight I'm very pleased to have Mike Curry presenting. He is a registered landscape architect and horticulturist with over 20 years of commercial and residential design, build, and nursery production experience. He's worked with the Midwest Trading as a sales consultant on growth media for nursery production, landscape soils and amendments, engineered soils, structural soils, and green roof media since 1999. He's worked on 7 million square feet of rooftops in Chicago alone, so he's got a lot of experience with that. He's responsible for business development, product development, soils consulting and specification, and is a member of Green Roofs for Healthy Cities, Growing Medium Committee, and committees for green roof design and construction courses and green roof professional accreditation. He's a graduate of Southern Illinois University in Plant and Soil Science, specializing in environmental studies. He serves on the SIU College of Agriculture Leadership Board, and he's also the current board president of the Midwest Ecological Landscaping Alliance, MELA.
Okay, welcome everyone. First I would like to just take a couple of minutes to give you a feel for what you can expect here. Soils are an enormous and complex subject, and my biggest challenges were to narrow this down to relevant info for the purpose of this webinar, and to keep the subject at an understandable level for everyone and within our time constraints. So to do this, first I'd like to review soil properties and characteristics in general, along with some definitions. I'll be going through these fairly quickly in order to spend a bit more time in other areas. Although we have people from many regions with very different soils, this info will be valid whatever the type of condition of your local soils. As we move forward, you'll see how important the basic soil information is in determining what your challenges are and how to amend some of the soil conditions you encounter. I'll cover quite a bit in much detail as time will allow, and that being said, we'll really only be scratching the surface. As was mentioned, we'll stop to answer a few questions a couple times during the presentation and at the end. I certainly don't have all the answers, but I'll do my best to answer your questions. You may also email me after the webinar. I'll have my contact info listed with the references at the end of the presentation. Since soils are not a real sexy subject, I've searched and inserted some graphics to keep things a bit more interesting. Some of these are better than others, so if the resolution is not so good, you just understand these have been, in this case, they've been used to illustrate the overall concept and may not need to be actually read on your end in terms of the typing, the print. So let's get started with soil composition. All right. For some reason, give me a moment. There we go. A little technical difficulty there, but the soil composition, ideal soil composition, I'm sure everyone's seen this pie chart. Wouldn't this be great? 25% air, 25% water. Mineral particles, 45%. And really what's unique about this pie chart that I haven't seen before is that it's interesting because it breaks the organic matter fraction down, talking about 25 or 5% organic matter, but 80% of that being humus, 10% being roots, and 10% being organisms. The soil ecosystem, it's important to understand the complex relationships within the living system known as soil. Soil environments vary by location, as we know, in terms of content, structure, and chemical makeup. Critical aspects of soil are physical properties, structure, texture, and density, chemical properties, pH, EC, CEC, CN, and nutrients, organic properties and organic matter, and soil biology. I'm going to go into a little bit of each of these. On the right-hand side there, you can see the soil profile, which is a typical natural soil profile. So at the very top, you have your highly organic humus layer, often referred to as the O horizon, and as you go down, you have the A horizon, which is rich in humus and minerals. B horizon, poor in humus, rich in minerals. Now you're down to the weathered rock in the C horizon and the bedrock on D. The physical properties, this is one of those graphics that's not real clear, but what we're looking at here is soil structure and aggregation, which refers to the arrangement of soil particles, their shape, size, and stability. So this plays a major role in how the soil functions. These large aggregations are called PEDs. That graphic you can see, although it's a little blurry, those are sand, silt, clay, and organic matter that are combined and kind of glued together in a PED. Soil structure starts with a particle, then you get the aggregate. The PEDs then form the overall structure. Now, these PEDs are held together in clumps. The structure is typically destroyed upon what we often do in terms of pulverizing and screening the topsoil, and it's also they're also often destroyed by compaction. Soil with good structure has stable pore spaces that allow water penetration, root growth, earthworm movement, and air storage. Soil texture, on the other hand, refers to the relative proportion of mineral particles of various sizes in a given soil. So there it gives the ranges of clay, silt, and sand, and there's a graphic illustration of proportionate size of particles, so you can see the sand particle is the largest, the silt quite a bit smaller, and then the clay very small. The interesting thing, though, is that with sand, in addition to these three basic sizes, you have very fine, medium, coarse, and very coarse sand. So within that sand percentage, you need to consider how fine the sand is. A lot of times this isn't considered, and you look at a sandy loam, say, oh, there's a lot of sand in there and it's going to perform a certain way. But if that's fine or very fine sand, it performs more like a silty soil. And very fine and very fine sands can clog up pore space and compact in soils just like silt and clay. Soil texture. Probably everyone's seen the soil triangle, which helps you determine where, once you have a particle size analysis, textural analysis of the soil, sand, silt, and clay percentages in that soil, then you can find where you land on that triangle. And this is important because we amend the soil differently depending upon whether we're dealing with a clay loam or a sandy loam or a silt loam or wherever it falls on there. You have a little different consideration. Permeability is the ability of water to move through the soil and at what rate. It's directly influenced by porosity. The number of pores as well as the size of pores affect permeability. Large pores allow for more movement and more readily available water for plant growth, but smaller pores do not. However, the largest pores are not necessarily most conducive to plant growth. Porosity is determined by the size, texture, and structure of the particles, as well as the type and distribution of organic matter. You're going to hear a common theme here on organic matter through this whole presentation. Soils with fine texture hold more water, but medium texture soils are actually best for growing plants. If we look at bulk density, is very closely tied to compaction, and it's a measure of the soil's mass per volume of soil. A lot of factors include this, or influence this, including organic matter content, porosity, and structure as well, and they control the hydraulic conductivity. A soil with a well-developed structure will become less dense as porosity increases, and as a result, the bulk density of soil will decrease. That little graphic on the bottom shows an illustration of the same soil that's been compacted, and of course you can see that the pore spaces have been squished out of them. Another point here is that dry soil resists compaction. Moisture enhances compaction to a point, and there's something called optimum moisture, which is often used in engineering in terms of determining what the optimum moisture percentage will be to get the optimum compaction. So there's a point at which the soil can have just the right amount of moisture to completely press all of the pore space out of. And then, of course, once you get beyond that, then you can't compact it. It becomes too liquid, and it just kind of smushes around. Chemical properties are very important. Chemical composition of soils affects how nutrients circulate through the soil environment, determines overall plant growth. Chemical composition depends on the pH, acidity content, soil structure, and the chemical activities that actually take place between the soils and the soil life forms and the plant life forms. Nutrients. Mineral nutrients are divided into macro and micronutrients. Macronutrients, which plants need in greater amounts, include primarily nitrogen, phosphorus, and potassium, as well as secondary nutrients, calcium, magnesium, and sulfur. Micronutrients, which plants need in very small quantities, include boron, copper, iron, and zinc. Salinity is also referred to as electrical conductivity, or EC. It's a measure of the level of soluble salts a soil contains. Problems with irrigated soils can occur when there are elevated evaporation rates and low rainfall, which in turn causes salts to build up. Buildup can also occur due to irrigation water, compost, manure, and fertilizers that are applied to the soil. It's possible to filter the salt by gradually applying surplus water. About 3 inches of water can remove 50% of the salts. 5 inches can remove about 90%. Of course, this is a function of porosity and drainage as well, but leaching the soil is a good way to get the salts out. One of the worst salts is going to be sodium, and high levels of sodium can result from poor drainage and soil compaction issues. Excess sodium in soil can impede plant roots from taking in important minerals such as calcium, potassium, and magnesium. However, you can manage high levels of sodium by maintaining optimum levels of calcium in the soil. Gypsum, in particular, is often used in acidic or salty soils to remove sodium and help balance pH levels. Irrigation with soft water can cause high levels of salt buildup. Of course, improved drainage and leaching helps to remove the salts. And just a note on how gypsum works. Gypsum is calcium sulfate. It helps to break up clay soils. The calcium binds to the clay particles and loosens the soil structure. And it also exchanges places with sodium, while the sulfate binds with the sodium and then takes it away as you leach it through. So a number that I've worked with in the past is 40 pounds of gypsum per 1,000 square feet worked into the soil, but it does take years. It takes several years to extract that sodium if it's built up significantly in the soil. pH, of course, is the acidic. It tells how acidic or alkaline a soil is. Plant roots won't be able to thrive outside a precise pH level, and it varies by plant. If the soil is too acidic or alkaline, the plant will eventually die. Neutral pH is 7. Acidic is below 7. Alkaline is above 7. Plants grow best in a pH between 5.5 and 7.5. Everyone's probably seen this chart. It's just a demonstration of the range of pHs and how it affects specific nutrients. But if you look at the range between 5.5 and 7.5, you can see that most nutrients are readily available during at those levels. You start getting below levels and the nutrients get limited, and that happens with too high of a pH as well. So if the pH, the nutrient can be there, but the plant can't take it up because the pH is too high. This one's interesting just because it gives you some reference of other types of materials and what the pHs are. Distilled water being 7, seawater being 8. You start getting up into ammonia, bleach, and lye are way at the top of the alkaline scale, and then lemon juice, battery acid down at the bottom. I thought it was interesting that that beer was slightly more acidic than coffee, and then orange juice and vinegar. Cation exchange capacity. The cation exchange capacity is the total amount of exchangeable cations that a particular material or soil can absorb at a given pH. These exchangeable cations are held mainly on the surface of colloids of clay and humus, again, organic matter, and are measured in milligram equivalents per 100 grams of material or soil. In general, the higher the CEC, the higher the soil fertility. That graphic, although you can't read some of the bottom table in the bottom, it's basically just illustrating. On the left, you have a higher clay soil with a CEC of 25, and you can see there's a lot more positions there to hold cations. If you look at the block of soil on the right, that's a very sandy soil, low in clay, low CEC of 5, and you can see that that has a much lower exchange rate. Carbon and nitrogen ratio. This is expressed as C to N. It's a ratio of the mass of carbon to the mass of nitrogen in a substance. The ratios are an indicator for nitrogen limitation of plants and other organisms. The carbon to nitrogen ratio for most natural soils is typically between 10 to 1 and 20 to 1. High carbon nitrogen causes nitrogen draft, which is basically pulling nitrogen out of the soil. As the organic matter decomposes in the soil, it requires nitrogen to feed the microorganisms. So if the carbon to nitrogen ratio is very high, there's not enough nitrogen to feed the organisms and to make it available for plants. So that's part of the reason why you're looking for a lower carbon nitrogen ratio in soil and in the amendments that you're adding to the soil. It's a good place to stop and take a few questions.
Okay, let's see if we've got a few questions here. One question is from someone who has a question about penetration of water in soils. They have a vegetable garden where water doesn't penetrate easily. It just drips off like water from a duck's back. And it seems as though there's some water-resistant substance in the soil, and this person wonders if you have any ideas what that might be.
Well, it sounds that often happens in a potting soil because it's there's components in potting soils like peat moss that become what they call hydrophobic. So when a soil dries out, and it happens with a lot of peat moss is a good example. When it dries out, it needs to have a certain moisture content in order to allow the water in. And as a result, if it dries out too much, it just runs off, like you mentioned. In a garden soil, you don't see that as often because of the mixture of the components that are in there. If there was a lot of peat moss that was blended in, that could be one thing. If the soil moisture is low, that could be a factor. there are wetting agents which allow more moisture penetration into potting soils, but it sounds to me like you need to add, you need to add structure to that soil, increasing the porosity to allow the water to go through.
Okay, great. I don't see any other questions right now.
Okay. Okay, good. So we're going to move on to the soil food web, which is critical to the health of the soil. We're going to talk about organic properties and soil biology. And as you look at this chart and kind of work your way through it, I'm going to explain a little bit of how this works. The soil biology, a soil ecosystem is loaded with living things, including plant roots, bacteria, protozoa, fungi, nematodes, arthropods, and earthworms. These soil dwellers form a complex food web. Fungi and bacteria decompose organic matter, and some kinds work symbiotically with plants, providing them with nitrogen or enabling them to absorb more water and nutrients. Most people are probably familiar with mycorrhizae. They act that way. Nematodes, protozoa, arthropods feed on fungi and bacteria. Earthworms improve soil quality in multiple ways, such as enhancing its aeration, disseminating nutrients and microbes, and intermingling soils from different layers. It's interesting because they work just like the critters in our guts and that we cannot live without. Soils are not alive without these functions as well. And when you look at microbes, there's actually a little fun fact here. There's actually 4 billion microbes per teaspoon, that's billion with a B, in a healthy soil. Soil's organic matter is derived from living things. Decomposer organisms in the soil break down the waste and remains of plants, animals, and other organisms. This process enriches the soil with nutrients such as nitrogen and phosphorus and create humus. Not only is humus a key component of the soil structure, it also retains water and nutrients that plants and other organisms in the soil need. The soil's ecosystem health depends on having adequate organic matter. So an ongoing supply of fresh organic matter is needed to replace what the living things in the soil consume. What we're going to talk about next and how we determine how we amend soils is based on soil sampling and testing. Now, this is an area that I don't see pursued often enough, and sampling methods in the lab you use will vary depending upon the material and what you're testing for. Of course, the things to consider are the things we're talking about: chemical properties, physical properties, biological properties, potentially toxic compounds, particle size and distribution, which would be a sieve analysis, structural capacity, depending upon what your purpose for testing is. Maybe they're in stockpiles, maybe these soils are in stockpiles, maybe they're in place at grade, and so on. So before we do any amending, it's important to understand that we have a specific plan of attack in line with what we are trying to achieve. Too often applications of the wrong amendments are applied or in the wrong quantities, causing more problems than existed to begin with. For example, adding fertilizers unnecessarily only to create additional expense or unneeded expense while polluting waterways with the runoff, or raising concentrations in the soil to toxic levels. This is why the soil sampling and testing is so important. Soil analysis is where you determine what tests, first you determine what tests you need and to be performed on the samples. You have to think about where you're going with this and decide which tests you want to run. You also have to determine what lab you will need to send the samples to, and part of that is because different labs do different types of testing. You need to be sure the samples are collected according to the quantity and method required by the lab and the testing to be performed. Certain tests require larger samples, some can use smaller samples. It's a good idea to have a conversation with the lab regarding that. And then you need to submit plenty of lead time for the specific project. That kind of goes, that's directed toward my contractors who like to have results faster than the lab is able to provide them. There's other specific things that kind of go along with some of these, and we're going to go into that next. Of course, there's a variety of different sampling tools, and you don't need to purchase all of these to do get a good soil test result. You can utilize an old-fashioned hand spade and a bag to collect your samples. That's, in most cases, you don't need anything special. Whichever tool you decide to use, the most important thing is the process you use, and we're going to explore some soil sampling process in the next few slides. Now, when you're sampling soil, you need to first determine, of course, where this crop is going to be planted. Whether it's vegetable crops or ornamentals or planting beds or whatever, you're going to take the samples from those beds and not worry about other areas. You're going to avoid unusual areas. There may be small areas that the conditions are different on that property than where you're going to be growing whatever it is that you're growing. There are some examples here on this graphic where maybe the compost was stored or fertilizer was, or there's wet areas that drain very poorly. You'll want to avoid those. You want to take the samples from the areas that are most similar and where you're going to be planting from. Now, the correct depth is about 6 to 9 inches deep, because you need to get down into the root zone, and that's really significant. For the annual perennials, most trees and shrubs are drawing most of their feeder roots in that top 6 to 12 inches. The other thing that I don't see happen very often is taking composite samples, and what I mean by that is that you can't just dig one little hole on a property and think that the soil is going to be the same everywhere on that property. So that graphic to the right is showing you that in that particular section, there's been 15 to 20 samples that, maybe this is a backyard, and you've pulled 15 to 20 samples from different locations so that you get a composite sample by then blending these little samples together thoroughly, and then you're going to pull out of that just the amount that you need, that you've discussed or determined by the lab based on the sample size, what the test is being run. Labs do things, many labs do things very differently, so it's a good thing to, they'll usually give you instructions. They might even provide you with a bag. It's always good to record where those samples came from, document everything so that when you get it back. You may have suspicions of one area of the yard that you're having tested, and you're only pulling samples from that area, and then you don't want to mix that up with another area depending on what you're planting there. This is kind of unique. Not sure how many people would get into this, but sometimes samples need to be taken from stockpiles, piles of soil, or soil blends. And one of the easier ways of doing that is taking a PVC pipe with a 45-degree angle cut on it and shove the pipe in, and then use that as a sample collection tube. And you would do the same thing where you'd collect numerous samples and compile them. Another critical thing is certainly reading and understanding the soil analysis report. This is often a challenge. It's detailed, it's complex, but to get but it can help you optimize the treatment. Using a soil analysis aids in using the right amounts of fertilizer, chemicals, and amendments basic understanding of the process and terms used in soil analysis report is required for using the report properly. Now, I know that you can't read all of this, but I've indicated the website on the reference area at the end of the presentation, so that I downloaded all of these from this A&L Great Lakes Laboratories. I use this lab sometimes for chemical testing, and you'll be able to see the variety of things that they do. It explains in more detail. Different labs use different methodologies in the way that they test things, and they report in different units, and that can be very frustrating trying to understand and cross over if you're using multiple labs, because it's hard to understand how to relate and do the conversions and so forth. So the other thing is that I've noticed that I could send samples to 3 different labs and get 3 different results, because there's a little bit, even though they're using the same methodology, there's differences in the way people do things. So it's good to use the same lab for specific purposes so that you get consistent results, you have a relationship with them, you can understand the results and discuss what your needs are and what you're trying to achieve. You may need to work with more than one lab depending upon what types of tests you're looking for. As I mentioned before, some labs might do nutrient testing, others and not do environmental testing for harmful compounds or heavy metals or various other tests that you might like to have run. So I've included the next few pages so you can use them for a reference. We can talk about them a little bit, but they do a good job explaining various items on the test reports and how to interpret them. And again, the websites are listed at the end of the presentation, and all of these sheets can be found there. So this particular sheet is going over a lot of the units, the report terms. It goes through a lot of definition of what they're talking about: organic matter, phosphorus, sodium, pH, buffer pH, CEC, soluble salts, and it gives a little explanation of how they're talking about it. Also will tell you, in this case, if you look at the middle, there's a table in the middle, and that's basically a table showing lime requirement to increase the soil pH. Now, in my area, we're always trying to decrease the soil pH because the pH is too high. I'll make reference to that later, but it really is very unique to the region that you're in. So, and it's different based on, if you can see, mineral soils, organic soils, and sandy soils, they're treated differently. So the lab can help you sort that out. A&L also has this interpretive guide for soil test reports, and a lot of this should cross over to other laboratories, but you may, like I said, you may want to talk about the units that they're using. But the general information is good. A lot of this is the same thing. Then they get into soil fertility recommendations based on what the results are, and you can ask the labs for recommendations. It's real hard, even for an experienced person, to look just at a lab test report and make final decisions on everything that they might want to do. This is a good table and information on what fertilizers to select, what rates to put down, something that, as I mentioned before, you can spend more money than you need to and actually cause yourself harm or the environment harm by putting the wrong thing down in the wrong concentration. The next thing we're going to talk about here is, actually I'm going to just make mention on this slide that everything that we're talking about, when you're looking at natural soils versus urban soils, of course, natural soils are usually pretty uniform across the site. They have natural horizons, they have adequate organic matter, nutrients, structure. They fit more into that category on that soil profile on the far right that we saw earlier. When you're looking at urban soils, you're working in the cities on sites, or even in suburbs where they've done mass grading and stripping of the topsoil. the soils aren't uniform across the site. They vary tremendously. There could be fill. Some of it may be native and exists the way it did. Some of it may be subsoil. You might have subsoil on top of a humus layer as you're digging through and you find the original surface of what was filled. Often there's layers that are removed or, like I said, mixed or missing horizons. Compaction is usually an issue. They could be anaerobic because they're compacted and there's not enough pore space for oxygen, low organic matter, and then especially in urban soils, we get into the environmental testing. There could be debris, toxins, environmental hazards that are there. I'm going to stop there for a moment and see if we have any questions.
Yes, we do have several questions. A couple people asked about the average cost of soil tests and how to sell that cost to clients. Apparently, for instance, in the Bay Area, soil tests can be very expensive, and the asker wanted to know how they should sell that value of the soil test to their clients.
Yeah, a lot of what I'm indicating here is really what I would use to sell the value of it. I'm not sure in different regions what the soil tests cost. Typically, you might be talking about, depending upon, it really is a function of what you're testing for and to what extent, but there could be $50 to $50 to $500 worth of soil testing that you might be doing, depending upon what it is. It could be more. You start getting into environmental hazards, and those could be several $1,000s just for that that test. But there's two things to look at. One is the expense of what are the inputs going to be? Can you control the inputs, the fertilizers, to better determine what you need to apply to that soil to bring it to where it is? You can do biological testing. I didn't mention that either. And determine what what the biological activity in that soil is. You could spend a lot more money taking a shotgun approach or not having a specific target and applying things than you would if you determined what exactly was there. So that's kind of a general answer, but I think that if you combine that with the fact that not only could you be spending more money trying to attack a problem, this helps you understand what your problem is or what the course of action would be. The other thing that it does is it helps to prevent further contamination of the environment, in the example of putting down excessive amount of fertilizer that may not even be needed. For example, in most regions now, there's limitations to what's allowed for the runoff. Nitrogen is usually the limiting factor because that's most mobile in the soil. The phosphorus has mostly been taken out of fertilizers around my area because there's such an issue with phosphorus, and potassium could be in levels that are actually inhibiting plant growth. So you need to know that rather than putting down a triple 14 fertilizer where all you need is nitrogen. Well, now you're paying for the phosphorus and potassium, and you could actually be paying for something that's doing harm to your yard and to the environment.
Great. Another question is, given the variability of soils sometimes in a small area, wouldn't a composite sample blur important differences in areas? It
could. It could. That's going to need to be a judgment call based on what your knowledge of that. I didn't have time to get into the whole site soil survey process, but what you would want to do in a nutshell is get your best understanding of that property and make a judgment call as to if certain areas need to be isolated and you don't want to mix those with other areas because you suspect something or you've identified a condition that you don't want to blend those samples together. Certainly keep them separate.
Okay. And then there's sort of a grouping of questions about how you kind of decide which tests you really need. For example, One person asks that they say they often specify mycorrhizal fungi in planting plan specifications, and she wonders if it's worth doing that, or are they unnecessarily complicating things for contractors. And someone else asks, how do you determine, sort of more in general, what tests you need?
Sure. Mycorrhizae is kind of a buzzword, and I love them. They perform a wonderful function. However, they're abundant in the environment. So really, the thing about those types of microorganisms and fungi is if the food for them is there, they will populate the area. Okay, so you can take a soil sample and test for the mycorrhizae. They can actually identify what they are, but there's several, I think several 100,000 different species of mycorrhizae that are very specific to specific plants. So, most what I've seen in the past is kind of a mixed bag of endo and ecto mycorrhizae, and you're kind of, again, it's kind of a shotgun approach where, yeah, it'd be great to put these in here, but you don't know which ones are really already there and which ones are going to be needed. So you can test for it, but what's more important is that you create a rich soil that will allow those organisms to populate that soil naturally. What was the other part of the question?
Just sort of how you determine what soil tests you need in general. When you're sending in a sample, how do you decide? Well, I think actually, in my experience, usually they have a set of things that a set of tests that they normally do as part of the regular soil test. But is there any other way to determine what specific tests you might want?
Yeah, it's going to be a function of what you're doing. Are you growing vegetables? You're going to want to test the nutrient capacity. You may want to test, depending upon where you're at. If you're in an urban environment, you may want to test for toxic compounds in that soil, because you're going to have those compounds potentially incorporated into the vegetables that you're growing. Really, it's the lab. The lab can give you some guidance, and they usually have combination tests where they're like, okay, well, this is a landscape bed, and they're going to do this, and this test, or it's a vegetable bed, and they would do this. They can give you some guidance. The other thing that is going to happen is that if you start a program of doing this, and you're working in the same region, you're going to start drawing conclusions on what you're seeing, and you're going to know, well, the phosphorus in this area is always high, so I don't need to test for that. Or the soil the soil is always a sandy soil, so I don't, unless I see something specifically different about this location, I know I'm dealing with a sandy loam. I don't necessarily have to do a sieve analysis on it, but it's really kind of working with the region that you're at, and talking to the lab. But you're going to notice consistencies in the tests and in the soils that you're working with. If you get into an area and you're normally a sandy soil, and then all of a sudden you've got a yard you're working in and it's a lot of hard clay, well, that would, to me, raise a flag that this is unusual, so I'm going to go ahead and test it so I know what I'm dealing with here.
Yeah. Okay. Great. Let me just see here. There's a good suggestion that people reach out to their cooperative extension agents to get the best value on sample analysis, because they often know, where good labs are for your region.
Absolutely. Yeah. Yeah, and I provided that A&L information just because I thought it was very well organized, and anybody can get on it. They've got all of those documents and more posted on their website, so I'm not necessarily I didn't have any intention of promoting their lab services, but they really, they are a good lab, but they have that information very well organized.
Here's another question. Would you consider agricultural soils as natural or urban soils, or maybe as a third category? This person's thinking of converting agriculture to residential.
Yeah, that's an interesting thing. That would fit more into the natural soils, but highly cultivated natural soils. So there would be certain things you would want to test for, depending upon if that land has been fallow for several years. We usually want to look at what pesticides, herbicides, and if you can get from the farmer or the previous landowner, they usually keep records of what has been applied. That's important to know.
Okay. And then we've got two questions about compacted soils.
Mm-hmm.
Let's see, one person has soil that's so compacted that they have an inch of humus that has washed down from erosion to where they were testing, and under that is sea horizon. Do they
Mm-hmm.
take the soil out to combine organic material? And then someone else wants to know how you would mix organic material into compacted clay.
Ah, perfect. Well, that's a good segue into the rest of the
Great.
presentation here. So, restoring soil in place. Of course, you're going to have, and I'll speak to that organic amendment and so forth as we go forward here. But the chemical changes, of course, you could have pH, compaction, or anaerobic conditions change that, nutrient deficiencies, loss of topsoil, contaminants. We talked about that already. One of the things you can do in your survey, your site survey or soil survey, as I like to call it, is visually examine and smell. Smelling the soil is actually a very good way to see if it's anaerobic because it smells like vinegar. You can test for suspected deficiencies. Maybe you have experience. Maybe the Extension Service understands that, in your region. Contaminants, if you suspect them. You usually want to know what the pH is. pH is a moving target to some degree, but it's more stable in natural soils. Of course, you always want to choose well-adapted plants that will tolerate the soil conditions, but organic amendment tends to correct all of these pH, nutrient deficiencies, structural problems. Organic matter amendment supports the soil organisms and restores soil life. It's one of those things that relates to that soil food web that we looked at. We need organic material in there to support not only the fungi, mycorrhizae, but all of those other things. And if the food is there, they will come. It buffers the pH. It moves the pH more toward optimal. Takes time. It reduces bulk density. We talked about that earlier, which is compaction. Improves water holding capacity. You can put too much in and make the soil soggy. So it's good to understand what you're starting with as far as knowing what to test. That would be one thing I would always test for is organic matter, just to get an understanding. And I'll talk a little bit more about that here in a minute. It improves soil structure, which is mostly the porosity and drainage, and it increases the cation exchange capacity, nutrient storage, and availability. Now, we just mentioned some of these things and the organisms. Now, what we said was the organic matter supports the soil organisms, but it's actually the soil organisms that are doing these things. They're creating the structure. They're recycling nutrients. They provide disease protection, biofiltration. When you're looking at bioswales, rain gardens, the erosion control, and stormwater detention and moisture retention. Organic matter kickstarts the whole soil ecosystem, providing food and home for organisms. What they do in terms of how do they create soil structure, well, there's all these secretions that come from these organisms, and they glue the clays, sands, and silts together into these little aggregates, and those aggregates are then bound by all the fungal hyphae, root hairs, and roots, and And those spaces are made by moving arthropods and earthworms and decaying roots, and that forms the PEDs we were talking about earlier. And then, as I said, when all the organisms are present, roots and water can move easily through the soil. You're going to look at organic matter in a lab test, and this is one of the things I want to talk about a little bit because there's so much confusion around this in terms of what percentage organic matter. And organic matter is reported on a lab test by loss on ignition. They basically burn the sample. They weigh it, they burn it, and then they weigh it again. By burning it, you're burning off all the organic, and you're calculating the percentage of loss of weight. And most composts, a lot of people don't understand this. If you took 50% compost and blended it 50% with topsoil, you don't have 50% organic matter. Most composts or organic matters in general are 30 to 60% organic matter, or conversely, 40 to 70% mineral. So you're adding a lot of mineral into the soil along with the organic matter. You need to know the characteristics of the materials you're working with, and what the CN ratio is, and the nutrients of the amendment, to match it to your plant needs. You may be shooting for, I work in this specific region, and I'm normally seeing organic matter contents in the generally in the 3 to 4% range. The darker the soil, typically the more organic it has in it. You generally don't see it in natural soils real high, but if you get a test result back that says, your organic matter is 1.5%, and they say, you want to bring it up to 5%, then you need to know what you're working with, what you're adding in there, and how much organic is going to contribute to it. This kind of gives a little bit of more explanation about that. Adding 10% compost by moist volume, this is kind of rule of thumb. Adding 10% compost, and composts vary, but like I said, rule of thumb, into a soil does not increase the soil organic matter by 10%. It raises the soil organic matter by only about 1 to 3%. And that's based on working it into the upper 8 to 12 inches of soil to mimic a natural profile. We're going to talk a little bit about coarse compost and pine bark fines, and where you would, in general, where you would use. I don't know what's available to everybody in their regions, but this gives you a couple of examples. Too much compost too deep in the soil profile promotes anaerobic conditions. So you really want to add the compost to the upper 8 to 12 inches of soil and rip a little compost deeper when subsoiling to restart the soil life. That speaks to the question earlier, where you're going to add some compost. When we say rip it in, there may be, it may be that if you're doing it by hand with a fork, you would blend some into that and then add some more amended soil on top, or some good soil with the amendment in it. What you're trying to do is break up the interface between the layers. You don't want that, and you're going to be able to amend bad soil, rocky, clayey soil, with compost and create a much better environment for the microorganisms and then subsequently for the roots. But if you get too deep into the soil profile, what happens is you don't have enough oxygen down there. It just ends up going anaerobic. Now, one size does not fit all. I mentioned this earlier, and here's our soil triangle again. If you look at the sandy loam side of things, that is a coarser texture soil. When you have a coarser texture soil, you go with a finer texture organic matter. You amend with a finer texture organic matter. When you have a finer texture soil, which is more in the silty, clayey, loam, silt loam area down here, you use a coarse organic matter. This might be a finely screened compost of some sort, worm castings. Another example over here, this may be a composted bark, pine bark or hardwood bark kind of coarser type material. And you're going to get better results if you're matching your amendment to the type of soil, which then speaks to, okay, how do I know what type of soil I have? That's sending a sample to the lab and getting a sieve textural analysis or a sieve analysis. This is one of the biggest misconceptions right here, adding sand to improve drainage. Sand does not mix well into existing topsoil. Doing so is not advised unless the sand is blended in using large equipment or at a soil blending facility. You pretty much have to take the soil and sand and blend them together. It's hard to do it in place. You need to use a coarse concrete sand. There's a ASTM number, CE33. There's FA2. It depends, pits in different areas call it by different things, but you're using a coarse concrete sand. That, in other words, I mentioned earlier that fine and very fine sand, you want to stay away from that. Use at quantities where the medium to coarse sand in the final mix exceeds 55%. What happens is a lot of times people will take maybe 10% sand or 20% sand and blend it into a soil, and the problem is that you could actually create concrete. You'll do more harm than good. You can make it self-compacting, and you end up with a worse situation than what you had anticipated, rather than better. Again, a reason to justify doing a soil test. pH. Back to pH. pH can be easily raised with lime, but too low is not typically the problem. And of course, I had this was based on my experience in my area. Our local sands are calcareous, which means they were formed off of limestone bedrock, and it increases the pH. Having too low of a pH is easier to deal with than having too high of a pH. When you have a high pH, you can lower it with sulfur products or aluminum sulfate, iron sulfate. The problem is that you cannot, if you have a soil that was derived from a dolomitic area, it will continue to creep back up, so you need to continue to treat it to bring the pH down. And ongoing long-term treatments can potentially create other soil toxicities. Another reason that speaks to doing some testing. If you're doing something like this, you need to pull a sample once in a while and see, once a year, better twice a year, to see what's going on. Of course, the best option, as always, is to use plants that are adaptable to that range, and this is just kind of showing there's an optimal range there. I want to speak a little bit to soil harvesting, storage, and placement. Because that ties into a lot of the other things we're trying to do here. And of course, if you're going to do any grading and you have good soil, it's good to get that moved to begin with. If you're trying to reuse that soil for some reason, store it covered, breathable fabric, coarse wood chips, put a cover crop on it, prevents weeds and erosion. You're preserving the soil beds by avoiding pulverizing and screening. This is really a standard practice around here. I don't know what it's like in other areas as much, but we tend to grind it up and screen it, and then you're busting up all those beds, and then they need to reform, and it makes it it destroys the structure of the soil right from the start. If you can, add the organic matter before you put it back down. Rip in the first lift to avoid interfaces that can limit air and water movement. That little graphic on the bottom is showing a rake that you can do it in a number of ways, whether you're using a fork in a small area and just busting that up first. But if you just layer one thing on top of the other, you create other problems, and the water and air don't move through that that area. Moisture content is critical. Don't work the soil when the soil's too wet or too dry. That goes back to the optimum moisture I mentioned earlier. This is some graphic showing placement. The old way on top where we filled a layer and then we ran back over it and put another layer on top. Basically, you're just overly compacting the first lift and you're creating an issue for yourself. You're better off using a method that's more like the bottom, where you're packing it in, you're running over the subgrade and packing it in, so you're not compacting it. Of course, when you do this, you need to leave it a little bit higher because it's naturally going to settle in, or you can use a lightly vibrate or hand tamp it as you go to take some of it out, but you don't want to compact all the airspace out of it. And that shows a little bit of rule of thumb when you're using sandy soils or loam soils, and you're going to get somewhere usually between 5 and 20% settling, depending upon the type of soil and how it was amended and what you're placing there. So in conclusion, soil is an amazing substance. It's a complex mix of ingredients: mineral, air, water, and organic matter, the countless microorganisms and decaying remains of once living things. Soil is made of life, and soil makes life. Those references, websites, I'll leave this up while we take some more questions if there's any. At the bottom is my email address. Feel free to email me if you have other questions or there's any way I can help. I'll try and find answers for you, direct you to where I can. Any other questions?
Yes, that was great, Mike. Let's see, just related to references, one person mentioned a soil web app from UC Davis. I don't know about that app. Have you heard about it?
Oh, that's great. Please email that to me.
Okay. So if the person who mentioned that app could send that or post it on the question page, we can send it out to everyone. One person asked about soils that are under concrete or asphalt, so sort of severely compacted soils, and what do you do about that if you want to make it into a workable garden bed?
Yeah, what I would do, obviously you're going to have the pavement, then you're going to have the pavement base, which was compacted to support the pavement, and then you're probably going to get down to the subgrade. What you could do is rip up that subgrade some, throw some compost, blend it in. What you're doing is blending horizons, like in the natural horizon that we looked at, and then add your good soil on top, which has some of that same soil or amendment in it, so that you're breaking up that interface I talked about, and you'll get better penetration down through the layers.
Okay, great. And then another person asked about whether tilling, how that affects the soil organisms in the soil.
Yeah, I don't expect that you're going to be doing a lot of damage to the organisms as long as you're not, you know, to what extent you're tilling. I imagine that if you were pulverizing the soil, pulverizing the soil to the point where you're damaging the microorganisms, you'd be damaging the soil also, and
Okay.
the physical characteristics of the soil also. So,
Yeah.
if you're cultivating or tilling, it's good to break that up, but don't pulverize it. You want to maintain the PEDs, and there's a lot of those organisms that are in those PEDs that haven't been touched.
And then there were a couple questions about sort of how long it takes for things to have an effect, for an amendment to have an effect, and also related to that, how long it will take for plants to show a response to something like low nutrients or extreme pH conditions. I think that's going to be very variable, but
yeah, that's really highly variable. If we look at some of that's a little easier to talk about. If you're adjusting pH, it takes several applications to begin with, over several years to really get it to where you want it. If you're if you're adding fertilizer, nutrients, those should be pretty readily available quickly, but the better soil life you have in place, the more more readily available the nutrients will be, because they'll be processing those and making them available in plant forms. If you're using, one of the things I didn't mention, I like pine bark fines. I did mention that, and the reason I like those is because over time, not only do they provide organic matter and break up and improve the structure of the soil initially, but they also over time break down, but they break down so slowly that they leave pore space in the soil after they break down, because they have a really high lignin content. So so they do several things. Now that's going to take, you know, a few years before they break down, so they hang around for quite a while. But every circumstance is going to be different, and it really depends on the circumstances. I wish I could say more to that one.
Okay. What are your thoughts on biochar?
Biochar, I've been playing around literally with that. I really like the concept. I first read about the terra preta in National Geographic, probably whatever it was, 12 or 15 years ago or something, and they're referring to the amendment in the rainforests and the agricultural societies that have those rainforests have such a very thin, unstable soil system. Now, the biochar, I've studied it quite a bit, and what happens is there's all kinds of different feedstocks that go into it, so you get different characteristics from it. If it's produced properly, which I think is around, you know, they cook it for a certain period of time at like 550 degrees. We've used activated charcoal in horticultural purposes and soils and filtration media for a long time. It's a similar idea. I love the idea of it. The fact of the matter is, everything that I looked at, there's inconsistencies. You have to find a good source. You have to have the test results so you can see what it is, and you need to use it to have the most effect. You would use it in a very poor soil. It doesn't appear to have any significant influence on rich soils. So if you looked at a good agricultural soil, it probably would have little or no effect on it, or a good planting bed soil. But if you then, you know, used it, I've seen pictures where they implemented it, cultivated it in on an agricultural plot, and they swept onto the roadside parkway where the soils were all compacted and clay, and the corn in the untreated area and the treated area and the normal soil, you could hardly see any difference, but you could see where they swept out into the bad soil, where the application was in the bad soil, it had a significant difference. So I like the concept. I think it has its places. It's very expensive, and don't bother using it on rich soil, because it's not going to really give you much.
Okay, interesting. We have one person who commented about using pine needles and pine bark, that in Missouri they have pine wilt there, and so their state plant scientist is recommending that it not be used because it can weaken trees and spread the pine wilt disease. So that was interesting. And then one other person asked about whether they, isn't pine bark very acidic, which I think it's sort of mildly acidic. But
it is very acidic, and it's one of the things that I use to help acidify the soils I'm working with, because that's what I'm trying, you know, that's one of the reasons I'm using it. So that's a good point. But if your soils are very acidic to begin with, you probably want to be careful about that.
Great. So I think that's pretty much all the. Oh, well, here's one interesting question. Have you ever worked with remediating cemetery soils?
No, that's one area I have not explored.
All right. Okay. So
I imagine they'd be pretty. They would be pretty nutrient rich, though.
I would guess so too. And then I guess the final question, we do have a couple people who have not had a lot of experience with soils that have been on the webinar.
Mm-hmm.
And so one person wanted to know, whether you have any thoughts for someone with a very basic understanding of soil, and someone else had earlier asked about good references if you're just getting into trying to understand soils.
Yeah. I can tell you that the book on the top of my reference sheet, Up by Roots, is a wonderful book. It's more geared toward trees, but Jim Urban gets into a lot of specifically soil-related conversation, and I've used some of his information in my presentation here. That's a really good book. There's another one that you can go on Amazon that I purchased off of Amazon. It's called The Soul of Soil, and I can't remember the author, but the book is a I'm looking in my office for it right now. The book is not a overly complex or technical book, but it's very practical. So that would be another one that I think would be good for you.
And I just want to thank Mike very much for an excellent presentation. I know I learned a lot, and hopefully we can have you back at some point to give more detail on some of the other topics that you're an expert on.
Oh, thank you very much. Thanks to everyone for attending.
All right. Well